All right, today we'll learn a new method called a LU decomposition method. For solving systems of linear equations. Okay, systems of linear equations. Last lecture we learned Gauss elimination method. Today we'll learn a new method called LU decomposition method. It's a slightly different method, and in certain situations it works better than Gauss elimination method. And we'll discuss later in which situations. Okay, so we are talking about linear system. Let me write down a linear system. Okay, so this is my linear system. In this lecture, I'll be writing a linear system very often in a matrix form. Okay, so how I can write it in a matrix form? I'll introduce a few matrices. First, I will introduce a matrix A. Matrix A is a matrix whose elements is this coefficients A11, NYN, and so on and so on. Okay, I create matrix out of these coefficients A11, A1N, N1, and N. Okay. Out of X, I can also create another matrix, X1 and Xn, all the way up to Xn. The same with matrix B, B1, Bn. All right. So using these three matrices, A, X, and B, I can write this equation in the matrix form like this. Okay. So for the rest of my lecture today, I will be very often using this form. All right. So LU decomposition method. What is the idea behind LU decomposition method? The idea is very simple. Suppose you somehow know how to decompose matrix A as a multiplication of two matrices, L and U. Okay, your matrix A, you decompose it as a multiplication of two matrices, L and U. This is where the name LU decomposition comes. Okay. All right. If you can do that, here is what we can do. Let's substitute this A into this equation which we want to solve. So it will be LU multiplied by X is equal to B. All right. Now I can split the problem into two steps. Here. Let me call this guy a matrix D. So first I can solve this equation and find matrix D, and then I solve this equation and find matrix X, vector X. All right. So this is the idea about LU. This is the main idea of LU decomposition method. First, you decompose A into L and U, two matrices. Then you solve this one, find D, where D is U multiplied by X. And then once you have D, you find X. All right. So each of these steps, this have their own names. This step is called decomposition step. This step is called forward substitution. And finally, this step is called backward substitution. All right. All right. So what is the point? What is the point of introducing a new method? The point is that this method works better than Gauss elimination method in certain situations. Let's try to understand in which situation. Okay. Here is a situation where it can work best. Okay. So here we have three steps, right? Decomposition step, forward substitution step, and backward substitution step. It turns out in many problems that appear in many different disciplines, you have to solve this system for different values of B. Okay. You have to solve this system for different values of different vectors B. Okay, A remains the same, but B may change for a problem. Okay, so you are solving a problem where your matrix A is given, but matrix P, there are different versions of matrix P. Let's say 1,000 different versions of matrix P. In that case, this step in this method, LU decomposition method, this step you do not need to repeat again and again because matrix A is fixed. This is fixed, okay? So this step, you do it once, and for the rest of the values of B, you just do these two steps, okay? That's the reason people invented this method. That's exactly for this kind of problem. A remains the same, but B may change. First, you may solve for one B, second B, third B, and so on, 100 different Bs. Let's move forward. Okay, so here is the idea. So in which case it becomes more efficient. It becomes more efficient. It becomes more efficient if these steps, you can make these steps very efficient, these two, okay? So what's going on here is that we decompose this matrix A, you have just one decomposition. The vectors L and U remains the same, You solve for 1B, you already have your decomposition. Now you want to solve for another B. This step you don't need to do. You already have your L and U. What you do is just these two parts. And suppose you do these two parts in a very efficient way. You come up with a very easy way of doing this part. In that case, this is where this becomes more efficient, let's say, than Gauss elimination method, which we discussed. All right, how we can do that? It turns out that we can do if matrices U and L has certain properties, namely L and U. Namely, if matrix U is upper triangular matrix, which is to say elements in this upper triangle is non-zero, whereas here it is 0. U means upper, so this is how you can remember it easily. L is a lower triangle, elements Lij and 0 here. Okay, if it turns out, if you can do it this and this way, if you can decompose A in these two matrices, which has this and that form, in this case, these two steps become really trivial, as we will see. These two steps will become really trivial. So solution of this large system with multiple B's boils down to doing decomposition once and doing these trivial steps multiple times for each of these B. All right? Okay, let's see how we can do it in practice. Right now, it sounds maybe a bit too theoretical, too abstract. Let's see specific example. Let me do it here. All right, I'm going to solve 3 by 3 system, which is a system of 3 equations with 3 unknowns. A11 x1 plus A12 x2 and A13 x3 is equal to B1, A21. Okay, this is the system I want to solve. I want to show this method in detail for this system. All right. So first step, we need to do decomposition step. Okay. First, we have to decompose this matrix A to L and U. Very good. It turns out, Gauss elimination method, which we discussed last time, when we do Gauss elimination, we actually automatically get both L and U automatically for free. Let's see how. So let's go quickly through Gauss elimination method. First we multiply this equation by A21 divided by A11 and subtract from the second equation. And then you multiply the same equation by A31 divided by A11 and subtract from the third equation. And we get this new system where we eliminate unknown x1, right? A22 prime x2 plus A23 prime x3 is equal to B2 prime. All right, so we eliminated x1 and we have this reduced system. Now I can multiply this equation, first equation, by A32 prime divided by A11. A22 prime. I multiply this equation by this guy and subtract from the second equation. And what do I get? What do I get is this another equation, but for x3 only. Okay. So, as I just said, Gauss elimination step already creates this decomposition. Let's see how. It turns out these coefficients, and these coefficients is already matrix U. All right? Remember, U is the upper triangle. So it turns out U is just A11, A12, A13, 0, A22 prime, A23 prime, 0, 0, A33, 33 prime. Okay, it turns out U has this form. Sorry? Exactly, double prime. That is U. We already have L now. We already have L here. L, it turns out, this is the first element of L, second element of L, and third element of L. Let's call it F21. Let's call this F31. And let's call this F32. So, what is the form of L? What is form of L? It turns out is the following. Along diagonals, we have ones. Here we have 0, 0, 0. All right? Here we have F21, F31, and F32. It turns out this is my L. And you can check, and I'm not going to show it, you can check that if you multiply L by U, you get A. All right? So elimination step is equivalent to LU decomposition step. Elimination step of Gauss elimination is equivalent to decomposition step of LU decomposition method. All right, very good. Very, very good. Now we decomposed. Okay, that's only step one. What was step two? Forward substitution, right? Let's do that step right here. Okay, so I obtained my matrix U. So let me remind all these steps. So this is the first step. All right, so original equation is this one. So I put LU instead of A. LUX is equal to B. So first I call it D. UX I call D. So I have to solve this part now, right? I have to find D. That's forward substitution step. Let's do that step. Okay? All right, very good. So let's do that. Again, for this system. L, let me explicitly write L. Okay, that's my L. D, some unknown D. D1, D2, and D3. And that's equal to B. B1, B2, and B3. As I was saying, this step should be trivial in order for this step, for this method to make sense, right? To be attractive. This step has to be really easy. And it turns out it's really easy. Okay, we need to find D. Let's find D1. Can you find D1 immediately from here? What is D1? It's just B1. D2, we multiply this by this, plus this by this, and this by this. That will give me B2, right? So F21 multiplied by D1 plus D2 is equal to B2. From this I find D2. D2 will be just B2 minus F21 D1. Very simple. I found D1 and D2. So the only thing to do is to find D3. So I equate this one to whatever is corresponding element. So which is this multiplied by this one, plus this multiplied by this one, plus this multiplied by this one, right? Let's write it. F31 multiplied by D1 plus F32 multiplied by D2 plus F plus just D3 is equal to B3. From this, it is trivial to find D3. D3 is just B3 minus F31 D1 minus F32 D2. Okay, I found D3. I found D. I'm showing it in three-dimensional case. Extension to more dimension is conceptually really trivial, right? I can write the expression for loop for this. And for loop will be, algorithm for generic n, where n is the order of the system, is the following. Di is bi minus okay, So for some generic n, where n is the order of the system, this is how you determine n. So it turns out it's just one for loop. It's trivial to implement it. Very simple. All right, I am done with forward substitution, and final step now is to find x from this part. Ux is equal to d, and from that I need to find x. Let's do that. Let's do that right here. Okay, so I'm doing the final step, backward substitution, ux equal to d, and I have to find x. Okay, the same story. Here is my matrix U, and I already found d. I have to find x. Okay, let's do it. Let's write it explicitly. Okay, let's write it here. Use what I wrote already. Okay, so this one becomes x1, x2, x3 is equal to d1, d2, d3. Okay, this equation I have to solve. So how do we solve it? Exactly. A3, 3 double prime, x3 is equal to d3. From this, x3 is of course this one. Very good. Now, I equate this element to the corresponding element on this side, right? Which will be this multiplied by this plus this multiplied by that. A2, 2 prime, x2 plus A2, 3 prime, x3 is equal to d2. x2 then is just d2 minus A2, 3 prime, x3 divided by A2, 2 prime. Very good. Now we have to find x1, for which I equate this element to the corresponding element on this side. A11 x1 plus A12 x2 plus A13 x3 is equal to d1. From this, x1 is d1 minus A12 x2 minus A13 x3 divided by A11. Okay, I found it. I found it. Again, I can write a generic form. I wrote it only for a system of three equations. I can write it for any generic n. Algorithm is conceptually trivially extended to multidimensional case. I mean, to the case of n equations. And this is what it is. For I is equal to n minus 1, n minus 2, and so on, all the way up to 1. Okay, done. All right. Okay, so we describe the system now, the method now. Now, let's see this. Let's solve one problem where this method is actually more efficient than Gauss elimination method. Okay, let's see one problem at least. And that problem is finding inverse of matrix. So we are given some matrix A, and we need to find inverse of that matrix. And it turns out LU decomposition method is particularly suitable for that problem, as we will see in a bit. Okay, so we need to find inverse matrix. Okay, let's remind ourselves what is inverse matrix. We have matrix A. Inverse matrix is such a matrix which is denoted by A minus 1, such that A multiplied by this one, independent of the order of multiplication, you get identity matrix. Okay, that's the definition of inverse matrix. This is a matrix which is inverse to A. Very good. Okay, so we are given matrix A. Let's find its inverse using LU decomposition method. All right. Very good. So let me ask you one question. I solved the following problem. Matrix A multiplied by unknown x equal to B. I solved three equations of this kind for three different values of I. Okay. First, I will solve for this I, B1, sorry, for this B, which is 1, 0, 0. Then I solve for second B, 0, 1, 0. And I solve it for third B, 0, 0, 1. Okay. So, and I get 3 sets of values of x, right? I solve for this one, and I get 1 set of x. I solve for this, I get another solution. I get for that, and I get another solution. Now tell me how those 3 solutions are related to inverse matrix. Exactly. So if I solve it with this guy, the solution of the system is the first column of this matrix. Okay, first column of this matrix. This guy is the second column of this matrix. Solution of this guy is the third column of this matrix. And I have it. I have my inverse matrix. Okay, now the question is, why we have to use LU decomposition method? Can't we just use Gauss elimination method 3 times and say 3 my solution? Why do we need LU decomposition method? Okay, let's remind quickly ourselves the general idea behind LU decomposition method. This is our problem. A with decomposers L and U. We do it once. So first, then we solve LD equal to B, and UX is equal to D. Okay, what's happening is our matrix A is given. We have to find inverse of that, right? So we do this step once. We decompose, we find N and U, and then repeat this step 3 times for each value of B. For each value of B. Okay? That's why this is more efficient. This is a case of the problem where the right-hand side of the equation changes. All right, any questions? Some of you may be asking, why do we need inverse matrix? Any ideas why do we need inverse matrix sometimes? In the context of the solution of linear systems, inverse matrix is useful, it turns out, to judge about the quality of the solution. Okay? As we learned last lecture, some systems can be ill-conditioned, which means the solution may be dominated by round of error. It turns out inverse matrix allows us to analyze that situation. How? Very easy. Very easy. So suppose you have this system, AX is equal to B. Okay? Now you want to judge whether this system is ill-conditioned or not. One thing you can do, once you find inverse matrix of A, you can look at this guy. Okay? You multiply with the inverse matrix and see, do you indeed get inverse identity matrix or not? Do you or not? If not, then maybe the solution is, the system is ill-conditioned. You are dominated by a round of error. Okay? That's one thing you can do. Second thing you can do, you can take inverse of inverse. Do you get matrix A or not? That's another thing you can check. So inverse matrix gives you ways of judging about error in your problem in different ways. But there is one way which is based on just one number. You can come up with one number using inverse matrix that tells you how good your solution is, gives you an idea about how good your solution will be. Or in other words, how ill-conditioned your system. And that number is called condition number. Matrix condition number. And it's denoted like this. For matrix A, condition number with this notation. Some time ago, we were talking about condition number, right? And for any numerical problem, we can introduce a condition number. Condition number tells you how much error in input translates to error in output. Okay? Error in input of your numerical solution multiplied by condition number gives you error in output. It works similarly here. Okay, so we are solving this problem. Okay, so So, and let's see how it works here. How condition number allows us to judge about the quality of our solution. How much round of error we have. Okay. So this is our solution. For example, matrix A, when we input into our problem, matrix A may not be known precisely, right? Matrix A. Suppose there is some error in A. Okay, so this is precise value of A. This is the value which we have. So we have some error in A. Let's call it delta A. So that delta A results to some error in X. Suppose this is a true solution, and suppose this is an approximate solution, plus delta X. Delta X is the error in the solution accordingly. So condition number allows us to relate error in input, which is error in A, to error in X. So it turns out this is how it works. Each of them are matrices, right? X is a vector, A is a n by n matrix. So this is how you can relate these two. It turns out the norm of X, and we'll discuss in a bit what is norm. Norm of delta X divided by X is equal to condition number in A multiplied by norm of delta A divided by norm of A. So what is norm? What is norm? Okay, and condition number is defined like this. Matrix condition number is just norm of A multiplied by norm of inverse A. Okay? What is norm? Norm is like a length. For example, you have a vector, let's say 3D vector, right? Some x, y, z. You can introduce a magnitude of that vector. Magnitude of that vector is just x squared plus y squared plus z squared. So this is a norm of that vector. Norm of the matrix is an extension of that concept. Okay? For matrix A, there are different definitions of the norms. The definition which we will use here is the following. It's just square root of I from 1 to n, j from 1 to n, aij squared. That's the definition of the norm. All right, so let's come back to this equation. So what this equation tells us? What? This guy, right here, this guy is a measure of relative error in the elements of A. Okay? These elements A have some error. And this guy, this ratio, gives us the relative error. It can be 1%, 10%, 0.1%, and so on and so on. Accordingly, this is a relative error in X, in the elements X. So that condition number relates these two. This one multiplied by condition number gives you error in. So if condition number, let's say, is 100, error will amplify by a factor of 100 when you're solving this. Which means the larger is the condition number, the more ill-conditioned the system is, right? Because it amplifies your error a lot. Large condition numbers amplifies a lot. So that's why this condition number, which is defined like this, just one number, gives you a good idea about quality of your solution, how well you can solve this given system. Okay? All right. And I want to make one final point here. Suppose you solved your system, and suppose that your condition number is pretty high. As a result, you get a pretty high error. Is there a hope to improve your solution or not? It turns out there is. Okay? Even if you have some bad solution, not very good solution, you can increase the accuracy of the solution by doing the following very simple but very smart algorithm. Okay? What is the algorithm? Very simple. Okay, so I want to solve this system. And suppose this is my approximate solution. Okay, I want to solve this system. Instead of exact solution, I get some approximate solution because, again, I have some errors. All right, so if I put this solution back to this equation, I do not get exact b, I get something different. Some b tilde. Okay, let me subtract this from that. And I get x minus x tilde is equal to b minus b tilde. So a multiplied by delta x, so this is delta x, right, is equal to some b minus b prime. Now, I have a new system here. Here are my unknowns. I can treat it as my unknown, and I can solve this system with LU decomposition again. I can solve with the LU decomposition very efficiently. Why? Because my matrix A remains the same. Because initially I solved it. I got this approximate x. I can use that decomposition, which I already did for that, to solve this equation and get delta x. Once I get delta x, I can add that delta x to my numerical error. Sorry, I can add that delta x to my estimate, numerical solution, which I already got. And if I do that, I get much precise estimate. I do not need to do it once only. I can repeat it, I can iterate it 2 or 3 times. Usually 2 or 3 times in my experience is enough. Any questions? All right, no questions. Thank you, guys.